Hi everyone, welcome for this sixth webinar with Xavier Levecq, our Scientific Chief Officer, and we'll are hosting to this morning webinar on a brand new technology that Imagine Optic just released, and it's the first demo ever on those two new products that Xavier will demonstrate in a moment. So we're gonna, sorry, I'm gonna go back to my computer to start the presentation. So this is more COVID compatible anyway. So this morning, Xavier will start by giving us an overview of what the LIFT concept is about and how we implemented that technology in our two new wavefront sensors. After this initial introduction, he will proceed to two demos of the new LIFT 272. And then we'll have questions. We're expecting that what we'll be presenting this morning will draw your attention and bring a number of questions on how to use those new devices in specific contexts. And then we'll have a closing remarks. So just a quick word about Imagine Optic. Many of you probably know us. We're a medium-sized company based near Paris with a subsidiary in the US and distributors all over the world. Our core business is in wavefront sensing, but we also provide adaptive optics solutions and manufacture deformable mirrors, along with optical metrology systems. We also do engineering and custom development services. So let's start with Xavier.
Hey, hello everyone. Thank you for being here with us today. So this morning I'm quite proud to present you this new technology about Shack-Hartmann. So let's have a look on first of all on the Shack-Hartmann, the standard Shack-Hartmann concept. So as you may know, Shack-Hartmann concept is the combination of a microlens array and a CCD, and each microlens of the microlens array intercepts a little part of the incoming wavefront and focalize as the light on the CCD. And the position of the spots behind each microlens give us the local slopes of the incoming wavefront. So Shack-Hartmann technology is sensitive to the first derivatives of the wavefront, and thanks to a mathematical integration, we can have access to the phase itself. The fact is that for Shack-Hartmann technology, the small part of the wavefront that is intercepted by the microlens is approximate to a pure tilt. That is to say that you can have at the end one phase point per microlens. Let's have a look now at we are on a Hartmann, and in this Hartmann, I have put quite high frequency contents in terms of wavefront, and as you can see here, you have some spots that are diffractively limited. That is to say that for those the approximation with a tilt is quite good, but some of them, for example, this one or this one, are not are quite deformed on the CCD, and that means that the wavefront that is just behind, in front of this microlens is not a pure tilt, but presents here some astigmatism and some coma. And this shape gives us a lot of information in terms of wavefront contents in front of this microlens. And all the story today will be about how using this information that is inside this spot, and more precisely inside the shape of this spot. Okay, so let's have a look now on this particular spot. This spot, for sure, gives us some information about tilts just with this position. And if you are looking what is doing in a standard Shack-Hartmann technology, the position is used in order to have the local slopes of the wavefront, and in terms of 1 microlens, this incoming wavefront is approximated by plane. Now, if we are able to use the shape and the deformation of the spot in order to have more information in terms of the incoming small wavefront here, and if we are able to calculate thanks to this spot what is a wavefront in front of the microlens, for sure we will have much more information in terms of high spatial frequency and in terms of this small wavefront that is incoming in front of this microlens. And that's the principle of the LIFT technology, the combination of the standard Shack-Hartmann technology with a phase retrieval, working with only 1 image at microlens scale in order to have the shape of the wavefront in front of each microlens. If you are able to do that, for sure, we will have much better spatial resolution and much more phase point with the wavefront sensor. Just to give you an idea of the sensitivity of this kind of method. This method of phase retrieval with only 1 image in order to have the wavefront in front of the microlens. Here on the left, that's the simulation of the diffraction of the microlens without any aberration. Here on the middle, it's the simulation of the diffraction of the microlens with only 10 nanometers peak to valley of astigmatism. And on the right part, it's just the subtraction of these 2 spots. And as you can see here, there is a specific and clear signature of the aberration of the astigmatism in front of the microlens. And now you know a lot about the LIFT technology. That is to say, how we are going to retrieve and to calculate the wavefront in front of the microlens. We are going to use spot subtraction. Just to give you a little overview about the signature of different aberration, you can find on the first line the signature of tilts in x-axis and y-axis. On the second line, you have the signature of focused, astigmatism at 45 degrees, and astigmatism at 0 degrees. And on the third and last line, excuse me, you can find here the signature of the third order Legendre polynomials. And as you can see here, all the signatures are different. And more than that, as we are using Legendre polynomials that are orthogonal over a square pupil, and the square pupil is the pupil of our microlens. We do have a signature that is orthogonal. So thanks to this signature, we are able to calculate quite fast and very fast the shape of the front of the wavefront, excuse me, the shape of the wavefront in front of each micron. So I won't go into the details of the algorithm and the principle of phase retrieval with only one image, but if you want to have more information about this, you can look at those papers, and in particularly, I propose for you to have a look on this first article from Serge Memon at Onera, who have made the first proof of concept of this technology for Shack-Hartmann wavefront sensor in 2014. Now, I would like to present you some proof and the transfer function of this Shack-Hartmann lift, the HASO LIFT, this new technology. For that, I have built a setup that is this one, and you have a photo here, where I'm going to use an SLM in order to put some holograms. And this wavefront will be analyzed with a wavefront sensor here. And with this wavefront sensor, we will be able to, for sure, to use a standard Shack-Hartmann reconstruction. And we will use the lift reconstruction too. And in order to have a proof of the spatial resolution improvement, I have built a second pathway with a zoom, a four times zoom, where I have put a standard Shack-Hartmann, and this Shack-Hartmann will give us, let's say, the truth. So the what should see this wavefront sensor with a lower resolution in the standard mode, but with enhanced resolution with the lift algorithm. Oops. So, as we want to have the transfer function of this new wavefront sensor, we have done something that is very standard, common, is to put some sinusoids with different spatial frequency. And like this, and thanks to this SLM, we are able to put this phase plates, let's say, phase sinusoids. And this wavefront sensor will measure this sinusoid. And this wavefront sensor with the 4 times zoom pathway will give us the truth, that is to say, what should see this wavefront sensor at the end. So we have begun with a very low frequency. In this, the period is 8 microlengths. And for sure, this zoom, 4 times zoom reference pathway give us the amplitude of the sinusoid that is a little bit more than 400 nanometers. And with no surprise, the standard Shack-Hartmann reconstruction give exactly the same value. And the lift reconstruction give also the same value. So everybody are agree on this. And we can say that for those three, the transfer function is 1, no problem. More interesting is this one, a very much higher frequency, and in this case, the period of the sinusoid is only 2 microlengths. The reference pathway gives us the amplitude of the sinusoid, that is 100 nanometers, and in this configuration, the Shack-Hartmann, the standard Shack-Hartmann, don't see anything. And let's see why. In this configuration, you can see how the sinusoid is seen by the microlengths. So 1 microlength see a part, the first part of the sinusoid, and this is a pure curvature. There is absolutely no tilt, so that means that there is absolutely no displacement of the spot behind this microlength. And the other microlengths see the opposite curvature here, and as there is no tilt, the spot is not moving. And in this configuration, it's absolutely normal that the standard Shack-Hartmann don't give us any significant signal. With exactly the same Hartmann prime, the same signal, the lift technology that is looking at the shape of the spots see the deformation of the spots, and thanks to this deformation can give us the information that this small wavefront is a curvature in one side with one side, and this is also a curvature with the opposite side. And thanks to that, we are able to reconstruct the sinusoid with the right spatial frequency and the right amplitude. So we have done that for all the frequency, and in a blue curve you can find the transfer function of the standard Shack-Hartmann, and the red curve gives us the transfer function for the lift reconstruction. And there is 2 points that are quite interesting here, is these 2 points. These 2 points are twice Shannon frequency for standard HASO here, that is to say 4 microlengths in one period of the sinusoid, and this one is the same twice Shannon frequency for the lift reconstruction. And you can see here that we have an resolution improvement by a factor of 4. So this curve gives us the improvement in terms of spatial resolution, and this spatial resolution is 4 in the 2 directions. So that means that in the 2 directions we have an improvement of factor of 15, 4 by 4, 4 times 4. So let's have a look now on the live demo. So I've just built a setup for this webinar, and this setup is a little bit simpler than the previous one. We have here a single mode fiber with a diode ladder, and the light is collimated on this SLM. This SLM is controlled by this computer, and with this computer I can send the hologram I want on this phase hologram I want on this SLM. So the light is coming back, focalized by this lens, and here we do have a beam splitter, and the light is going on this HASO LIFT 272, and this wavefront sensor will give us the wavefront sensor. One thing here is this wavefront sensor can work with the two modes. It can work in standard Shack-Hartmann with standard Shack-Hartmann reconstruction, and for sure it can work with the lift reconstruction. So let's have a look on the result and on the software. So you can see now my screen, and we have here the reconstruction of the incoming waveform here on the Shack-Hartmann. The resolution,
and this is Wave View 4, by the way.
Yes, the new it is the new software for wavefront metrology at Imagine Optic here. So the resolution in standard Shack-Hartmann mode here is 50 microlengths by 68 microlengths. So basically here we do have something like 48 by 48 microlengths that are lightened. This wavefront sensor is optically conjugated with the SLM in order to have the shape of the waveform at the output of the SLM. So there is nothing on the SLM right now, and you can see that we have a small aberration. Pretty, just the aberration, the residual aberration of this edge. And now I will put a Siemens target as a phase plate here, and a Siemens target is a standard target that is used for controlling the transfer function. It's a standard way to control transfer function in optics. And here you now have the reconstruction given by the standard Shack-Hartmann way of acting. And as you can see here, I have a little button to activate or deactivate the lift reconstruction. And now you will have the result of the lift reconstruction. And it is quite impressive that how the resolution is improved. Let's have a look again without the lift reconstruction and with the lift reconstruction. You can see that the edges are much more sharper. We can go much further towards the center of the target. Once again, I love that. And with the lift. And just have a look on the Hartmann itself. So I remove the pattern, the SLM pattern, and I zoom on the Hartmann, so the raw signal given by the wavefront sensor. And here you can see that all the spots are diffractive limited, without any aberration in front of each microlens. That's the case when you have an encoded wavefront without high order frequency. Now I activate the SLM pattern, and you can see that some of the spots are quite diffractive limited. So for those ones, the assumption that the small wavefront in front of each microlens is achieved is true, but for some of them, it's obvious that the shape is not diffractive limited anymore, and there is a specific deformation, and the analysis of this specific analysis shape deformation can give us the shape of the microlens, of the wavefront in front of the microlens. That's what we do when we do this reconstruction between the standard way, where we assume that each small wavefront in front of each microlens is a tilt, a pure tilt, and when we calculate the shape of the wavefront in front of each microlens. So let's have a look now on another pattern. And in order for me to show you the improvement in terms of resolution, I decided to show you a natural image transformed in phase image thanks to this SLM. And I will show you as an image the image of a monkey. Let's put this monkey. So now you can see the monkey with the reconstruction, the standard Shack-Hartmann reconstruction. And now I will activate the lift reconstruction, and you can see the improvement. And here, this natural image have a wide range of spatial resolution, low order and high order contents. You can see that the lift reconstruction gives us much more details and give us the information of very high spatial frequency on the image. Once again, yeah. And in order to finish this demo, I would like to now show you something that is more optical. And here I will put on the SLM a diffractive pattern, diffractive lens. So I have put the diffractive lens, and you can see the rings of the diffractive lens here, and you can count 1, 2, 3, 4, between 4 and 5 rings in the standard Shack-Hartmann reconstruction. And when I activate the lift reconstruction, it's clear that we can go much further. And now we can count the 8 rings that are present in this wavefront. So this is more is closer to a standard optical metrology than the monkey. But both of these patterns show us the improvement that is given by the lift reconstruction. Let's now continue the slideshow.
Yeah, actually, we have a question. Maybe you can answer that right away. Malek asked, can the concept also work with a polychromatic source?
Yes, it's a good question. You know, this concept was developed by Onera in 2014, as I said before, and these guys have developed this for astronomy. And for astronomy, they are working with white light, and this concept is working also with white light without any problem. So here, for sure, on this setup, you are working with white monochromatic light, but it can be used for polychromatic light too.
Thanks. So we're moving back to the end of the presentation. Feel free to ask more questions using the Q&A in the tool you have on the right corner of the screen.
Yeah, and as Patrick told you at the beginning of this webinar, we have decided to launch two products with this technology. So the first one and the smaller one is the 272 that is present on this demo page, and the other one is the big brother of the 272, and this brother is the 680, the 680, and the spatial resolution, the number of phase points that is given by the 272 is 272 times 200 phase points, and the resolution of the big one is the lift 680, and the resolution is 680 times 500 phase points. So it's more than 340,000 points. So it's huge. It's a huge resolution. It's the biggest resolution you can have with this kind of wavefront sensor on Shack-Hartmann technology.
So back to the presentation.
Yeah, and just to show you a result of this 680 HASO LIFT 680. I decided to show you the monkey. So on the left part, you have the image that is sent as an hologram to the SLM. Here in the middle, you have the reconstruction given by the standard Shack-Hartmann. That is to say that is limited by the number of microlenses. So in this image, it's about 100 by 100. And on the right part, here you do have the reconstruction given by the lift. And as you can see, it's absolutely obvious that the improvement of spatial resolution is huge. And here we are very close to the initial image. Just to give you some information about the resolution. So this SLM and this image, this hologram presents 800 by 800 points, And in this image, we have the reconstruction with about 400 by 400 phase points.
I have another question from we. Is the phase retrieval dependent on the wavelength of the incident light?
Yes, it is. When you want to use the lift reconstruction, it's necessary to give the information of the wavelengths, if it's a monochromatic wavelength, and if it's not, if it's polychromatic, you have to put the central wavelengths information.
Thanks. So feel free to write questions in the Q&A, and if you'd like to speak out, just raise your hands. I'll let you speak. But maybe we'll now finish the final steps of Xavier's presentation.
Okay, so now I would like to give you some example of application and the new application that are allowed with this new technology. So it's application where accuracy, dynamic range, and spatial resolution are quite important. So for sure, this kind of wavefront sensor are perfect for freeform optics. And because for freeform optics, it's necessary to have a very good accuracy. And here we present this wavefront sensor as a lambda over 100 accuracy. It's very important to have a huge dynamic range because freeform optics are often presenting a lot of a big shape variation. And for sure, the spatial resolution is also a key point. So the interest of this kind of wavefront sensor is that the best of the two worlds. Let's say the two worlds are the Shack-Hartmann technology itself, where you will have the perfect accuracy and a huge dynamic range, and this combination with this phase retrieval algorithm gives you the spatial resolution. So these wavefront sensors are very useful for meta surface and meta optics characterization, mainly because this kind of wavefront sensor is not sensitive to polarization. So that means that this wavefront can measure any polarization state. And for sure, and as we have seen in this demo, it's very useful for diffractive optics, DOE, and phase shift characterization. And in a general point of view, this wavefront sensor are very useful for middle and high spatial frequency characterization. Thanks this high spatial resolution, it's very useful to use this this kind of wavefront sensor for detection of small defects. And for that, it's possible to use this wavefront sensor in order to see, for example, the laser impact consequences on some optics. And for sure, it's all thanks to this to its spatial resolution. It could be used also with quantitative phase imaging. Okay, in order to have a wide range of application for this wavefront sensor, we have decided to have this technology compatible with our airflex system. So the airflex system is a self-illuminated wavefront sensor. That is to say that we put here a single mode fiber with a diode laser, and we do have here the light coming out from this system, and the wavefront sensor is measuring the incoming wavefront coming back from the optics here. And as you can see here, we do have a mechanical positioning here with a magnet in order to have something that is very stable and very reproducible. And let's have a look of the use of this system. So this kind of system can be used for concave mirror or parabolic mirror characterization. And thanks to the spatial resolution of this wavefront sensor, you can have access to high spatial frequency and middle spatial frequency, and for sure you will be able to have access to the residual shape error at high frequency. It can be used to characterize complex optics. Here, for example, is a telescope. And this telescope is characterized in double pass configuration. So the light is coming from the light source here, and is sending back thanks to this flat mirror, and the wavefront sensor is measuring the aberration in double pass. And last but not least, this wavefront sensor, and thanks to the WaveView 4 software, you can measure and characterize simple or complex objective in double pass configuration on axis and off axis, and get, for example, aberration, but also MTF of the objective. And the main improvement of using the LIFT technology for that, is to have access to high and middle spatial frequency characterization of those objectives or lens. We we have decided to also have this compatible with our Airflex LA system. So basically, the Airflex LA system is a collimator, and you do have one here. And this collimator is compatible with the Airflex 2 system. And we have the same kind of magnetic mounting holder for the Airflex system here. And thanks to that, you have a collimated light coming out of this system. And thanks to a flat mirror, can go back, and the system you will characterize, the flat mirror, for example, here, can be characterized in double pass with this system here. So as you can see, this system is looking like an interferometer, and basically you can do everything you do with an interferometer. And thanks to this high spatial resolution given by the LIFT technology, this system presents all the advantages of an interferometer, that is to say, high spatial resolution and very good accuracy. But thanks to this technology, you do have more than an interferometer, because with this, now you can have a system that measures in only one image, so it's completely insensitive to vibration. And last but not least, you can choose the wavelengths you will put here, and you can choose the wavelengths to characterize your sample you want to characterize. So that means that with this system, you have access to the application you could have with a multispectral interferometer. So let's have a look of what you could do with a multispectral interferometer.
Sure, and then we'll have a couple of questions.
yeah, just excuse me, with a multiple spectral interferometer, you could characterize a mirror at the right wavelength for the coating. You could characterize filter at the right wavelength, and so you can characterize filter in reflection and in transmission if you change the wavelengths. And for sure, you can characterize dielectrics at specific wavelengths, in reflection in the spectrum where the dielectric is effective, and in transmission in the spectrum where the spectrum the dielectric is transmitted. So yeah, let's.
Okay, that's a good question. So I have Klaus Mantel. I'm gonna open your mic, Klaus. Go ahead. Actually, I think you have to unmute yourself.
Yes.
Okay, go ahead.
Hello. Hi,
Hello.
I'm Klaus. I'm Klaus from the Max Planck Institute for the Science of Light in Erlangen in Germany.
Yeah.
Thanks, Xavier, for your very nice presentation.
You're welcome.
So my question is, I'm usually, or for the last 2 decades, let's say, from interferometry. And first question, do we need any interferometers anymore in the optical lab after your LIFT sensor? And the next question is more technical. How many pixels per spot do you need for sufficient accuracy in the reconstruction of these local wavefronts? And of course, I think you would also squeeze in more micro lenses into the micro lens arrays. But then maybe when the lens sizes become too small, you have diffraction more and more heavily, and maybe then your signal to noise ratio goes down. So what are your thoughts?
Okay, so let's begin with your first question about interferometry. Yes, with this kind of system, that can replace. I think that can replace interferometer in many applications with a lot of advantage, because it presents a lot of advantage compared to standard interferometer. And at the end, this technology is cheaper than interferometry. So we hope that this kind of system will replace part of the interferometer in the optic field. And now about your question, technical question. For sure, we need some pixels into the spot, and we are working with about between the minimum number of pixels that is necessary to make the reconstruction is about 3 pixels into the diameter. That's really the minimum. When I say diameter, it's from 0 to 0 on the cardinal sinus of the diffraction pattern of the square microlens. And it's perfect with a number of pixels of about 5 or 6. And to answer to your question about diffraction, yes, for sure, we need to have good isolation between microlens and between spots in order to not be influenced by the diffraction of microlens number 1 compared to microlens number 2. And for that, it's necessary to have something like about 20 pixels separation between 2 microlens.
Okay, so I have a couple of questions from the Q&A, and then I'll hand it over to Vicentiu, who's raised his hands. So first question, is there going to be a way to rewatch this? Absolutely, Oliver. It will be on our YouTube channel early next week. We just need time to edit and add the subtitles to it. And it also will be on our website. I'll make sure you get the info. Now, a question for you, Xavier. If I remember well the lift concept, one needs to introduce a small astigmatism for the face retrieval to work well. My recollection might be wrong. Sorry if this is the case.
No, you are absolutely right. It's not necessary to have astigmatism, but it's necessary to have aberration carrier on the migrant. And this is necessary, and it has been shown by several researchers in the past. And especially, I give you an article from Gonzalez and Gonzalez, pardon, Gonzalez, and the second, I remember it's the second article I give you as advice if you want to learn more about chip technology. And it's necessary to add a carrier, a phase carrier on each microlens in order to avoid what we call the ambiguity on focus, for example. Because if you have absolutely no aberration, no carrier on the microlens shape, when you have focus around the base plane, you won't be able to know the sign of the focus. So it's necessary to introduce some additional aberration in order to remove this ambiguity on focus, on even more generally on even polynomials. So it's necessary to have this carrier, but this carrier is not necessarily an astigmatism. And you're right, in the past, people that have worked on this subject have introduced astigmatism as a career, but here we are not working with astigmatism because astigmatism give some deformation of the spot that is not symmetrical. So it's not so good for Shack-Hartmann technology because at the end the accuracy is not the same on both directions, X and Y. That's why we have chosen another carrier, and not estimated carrier that is put on a very high order Legendre aberration and symmetrical.
Thanks, Xavier. So another question, when inserting some face jump object, does the mask automatically recognize the face map, or a prior mask should be selected?
Now to answer this question is how sharp is the jump? As you know, this kind of wavefront sensor is sensitive to the first derivative, to the slopes of the wavefront. So if we imagine to have a step that is absolutely perfect without any ramp and a pure step, for example, a 2 pi step with a perfect translation, I think that in this case, this wavefront sensor could not detect it perfectly. But honestly, I don't know. I don't know this kind of pure step. And as you may know, with the SLM here, we can try to reproduce this kind of thing. And it's what I've done with the Siemens target here that are jump. But even with this jump, the transition is not just pure, and there is a small. It's continuous. It's continuous, and if it's continuous, the wavefront sensor can measure it, and it's what we have done here.
Vincent, does this answer your question? Because you also raised your hand, so I'm gonna I demuted you. If you want to open your mic, and you can ask another question if you have one.
Yeah, thank you, Xavier. Thanks again for the presentation, a very good one. And I think we know each other. I actually used recently this kind of new high resolution wavefront sensor, which is very good actually. It's much better than the one we had. And yeah, my next question is for what is the maximum full aperture of this system with Airflex and LA 100 that can be used? Let's say we have a big mirror that we want to qualify, and as you said, this might replace an interferometer. So I want to know what is the maximum full aperture that I can use.
Okay, so we have developed this for a different diameter, and we have developed a diameter system for diameter of 30 millimeter, 75, 100, and 150.
Okay, okay. And my second question, it's a little bit different. So let's say, as you know, at Eli we have MP, we have high power lasers, ultra short pulses, and we want to, let's say, to characterize these pulses either in focus via different methods or in different configurations. But let's say one of our colleagues raised the question that if you have, how does the lift method act when you have, let's say, perhaps you have different wavefronts for different frequencies?
I'm not sure I perfectly understand your question, but if your question is about the capability of this wavefront sensor to accept convergent or divergent beam, what I can say is that the lift technology doesn't limit the capability of the Shack-Hartmann technology in terms of curvature. That is to say that you can use this kind of system with very divergent or convergent beam. For example, this one you can have a focalization point that is 50 mirror in front of or behind the macro lens array. So you can work with a different numerical aperture and different convergent or divergent beam.
Mm-hmm. And if I may, one last question.
Yes.
I know that in interferometry you need a reference, usually, and probably the previous caller mentioned that or didn't, but you need a reference. Let's say if you want to qualify a certain optical element, how would this HASO with Airflex and LA would, let's say, compensate for that reference?
Okay. So, for example, you would like to qualify a flat mirror, right? The first thing you have to do is to qualify the optical quality of this. So for sure, it's not perfect optical quality because it's standard optics with polishing. So there are some residual error. So the first step is to qualify that, and to do that, you will need, as in interferometry, you will need to have a reference mirror. And this reference mirror will be placed here. Before you qualify your mirror, you have to place your reference mirror here. Take the measurement of the aberration here. Put this measurement as the reference in the software, and then you will replace the reference mirror by your mirror, and you will take the wavefront measurement of your mirror, subtract the reference of the aberration of all this, and you will have the shape of your mirror. So it's the measurement is in two steps. So the first step is the calibration of the aberration of this, and the second step is the measurement of your sample. For sure, the recurrence has not to be done every time, because once you have qualified, once you have the aberration of all the system, you can remove it, remove and subtract it to all your measurements you will have to do. But it's necessary to have a first calibration of the system.
Thank you,
Okay,
Xavier.
okay. Thank you very much.
I hope it answers your question. I just want to mention the fact that we've reached 11, so we still have a number of questions in the Q&A, so I'm going to ask them, but feel free to leave if you have to. You can submit questions. We'll answer all of them, and they will be in the video recording available on YouTube. Now, if you have time, we're here, and we're happy to answer questions. If you want to leave and ask a question before you do, please raise your hand. So Vincent, sorry, I thought you had another question, maybe?
No. It's okay. It's okay. Thank you. Thank you very much.
You're welcome.
Thank you.
Another question from Pierre Madec. What is limiting ultimately the resolution and improvements you can get? And then there's another part to the question. It should be linked to the number of modes you can extract from each sub-aperture image, right? Is the limit coming from the field of view of each sub-aperture or anything else?
Hello, Pierre. I'm happy that you are here. So the limitation is, you're right, it's the number of legendary we can have access. And as you have maybe seen in the signature of legender, the signature of legender for low order legender are on the main lobe, main spot of the focal spot. And when you are going further in legender modes, the signature will be on the first ring, and then on the second ring, and then on the third ring. And the limitation is for sure the signal to noise ratio, because the light on the first, second, and third ring are much less than the light on the main spot. So that's why we are limited in terms of number of legender we can calculate accurately. And what we wanted to have here is not to reduce the accuracy of the standard Shack-Hartmann technology. That is to say that we want to keep number over 100 accuracy. So that's why the number of legender we are calculating limits us for now limits us to a spatial resolution improvement of a factor 4 only. But it's already huge.
Thanks, Xavier. I'm browsing through the questions. There are many of them, and I'm sorry some of the attendees had to leave. But again, we're going to go through all and every. Klaus, I think we already answered your questions because you took the mic. I have a question from Wei Xiong Wei. What is the frames per second for lift?
Okay. There is two answers. One is given, one answer is given by the speed of the camera itself, because we can record at the speed of the camera, and then we can post-process in order to have the movie, let's say, movie of the evolution of the wavefront. And then you are limited by the camera itself. So for the 272, the limitation is 20 Hertz. And for the 880, the limitation is 30 Hertz. And if you want to have a live reconstruction with a good PC like this one, it's a standard laptop, but a good quality last version, you can reach a frame rate of about 4 Hertz with this one, and a little bit more than 2 Hertz with this one, with the big one.
Okay. How long, it's a related question. How long does the phase retrieval process take additionally?
Yeah, so it's I think I've already answered this question, but it's relating to the frame rate. So for this system, it takes about 50 milliseconds to calculate for the whole sensor, and for this one it's no, for this one it's 25 milliseconds, so it's about 4 hertz, and for this one it's about 50 milliseconds, and it's really depending on your on the power of your computer.
Thank you. So another question: would lift work when there is speckle effects, for example, from scattered beacon?
Yes. You know, as we want to, as we are calculating the small wavefront shape in front of each microlens, thanks to the deformation and thanks to the information that is given by the shape of the spot itself. It's necessary to have a good quality of this spot, and for sure, scatter or diffuse in wavefront are often not presenting the optical quality that is necessary to have a good reconstruction. So I would suggest to no, it's really better to have something without any scatter. So
another question.
The wavefront we have to mirror.
Sure. Another question from Ivo Busk. How many mixed phase modes over one single micro lens are you able to reconstruct?
Enough to have an improvement of resolution of a factor of 15, 4x4. I won't go deeper on this kind of information for sure. So, but for sure, it's enough to have an improvement of 4x4.
Thank you, Xavier. So we have another question from Pierre-Yves, but I'm going to go through two questions from Aude Conté, who left earlier. For the defect detection, what would be the typical defect size detectable?
Can you repeat, please?
Sorry, for defect detection,
yeah,
what would be the typical defect size that this system can detect?
Okay, what we can say is with this kind of system, both of them, the phase point resolution at the position of the micron side will be around 20 micron for this one and 25 micron for this one. But for sure, it really depends on the magnification you will have in front of this system. So if you have, for example, a magnification of 10, and for example 10, and as the resolution is, for example, this one 25 micron at this position, with a magnification of 10, you will have a resolution of 2.5 micron on your sample. So what we can say is the resolution at the microlens position, and then you have to add the magnification. So 20 micron for this one, 25 for this one.
Thanks. So the second part of the questions was meaning without additional magnification. It was a separate question. Sorry, I didn't see it right away.
Okay.
And so you basically answered the question.
Yeah.
So it's going to be 25
Times
and 20.
times the magnification.
So thank you. I think we answered all your questions. Now, Pierre-Yves, so last questions. The live demo was really impressive. Thank you. On the last example, the diffractive lens, so I had the feeling that it was possible to see in the background the print through of the square geometry of the Shack-Hartmann. Do you get any residual or aliasing propagated into the reconstructed face?
We try not. We try not. For sure, it's a metrology. We are making optical metrology, and we have a limitation. And what we can say is that all our artifacts are lower than lambda over 100. But for sure, you as any metrological system instrument, you have a limitation and some noise and
Thank you very much for answering the questions and for participating this morning. Our next webinar should be sometime in June, so we'll keep you posted. And there will be further announcements on the LIFT technology in the coming months, but this is all we can say for today. So, bye everyone.
Thank you. Bye everyone.
Stay safe.